And then, yeah, so we start with machine translation. And again, let's see how much justice I can do within the next hour. It's a very broad topic. And yeah, so this chart is just introductory. It tells you that you might have seen for image classification or earlier the percentages were, maybe even lesser, like 50, 60s, and then they went up to 80 or something across a few years. So many of these problems which involve text, speech, or images have similar curves. When deep learning-based approaches were applied to them, you could get much better performance results as compared to the earlier where people used to write these rules by hand. Okay, so the machine translation, the most popular statistical machine translation, even though neural machine translation is also statistical, but the in the rule-based world, the approach was already called statistical machine translation. And there are a number of approaches which looked at phrases in the sentences to translate, or words, or syntax trees to translate. So, but this basically graph shows that the syntax based was growing. Phrase based was growing this way, but neural methods were introduced 2015, 2014 papers, and they suddenly took over, and it's 30 and 40 range. There's a particular metric that we'll talk about. But yeah, so that gives huge motivation for studying these methods and applying them to translation. Okay, so formal modeling, probability of the target sentence giving source in one language, target in another. And again, we're talking about probability because there could be multiple target sentences. You think of all the sentences in the target language as a set, and you want to assign weights to them and pick the best one, the highest weight. Okay, and so this is English to French, and it is useful to look at some examples to figure out if you had to write rules, how would you go about it? So roughly, you see that roughly the words correspond to words. The reason that these languages have similar languages are similar in some sense. So the maps to le program has been, there's something strange here, implemented, goes down to 3 words. Okay, so the first thing that you have lost is equilength. The input and output may not be similar. Output can in fact be smaller or bigger than. Okay, and the other thing that you have to learn is correspondence between word, input word, and output word. So here one input word corresponds to multiple output words. So you might have to learn functions like that also. Okay, some more example. This is, and it gets more complicated. That was, I think, one of the simpler examples. So now I can't pronounce French. Le prix de Nobel de paix. This is the input sentence, French. You want to convert into to receive the Nobel Prize. Okay. And this is sort of alignment setup. Okay, what happens? This and to one-to-one matching, they are both in the beginning of the sentence. Again, these two words have mapping, le and the. Something strange happens here. Now, if you had to convert this phrase, Prix Nobel de la Paix, to Nobel Peace Prize, what would you do? What are the operations that you need to do? So that's the problem, right? This sentence. So if you look at the word pre, that has prize. That's what it means. So prize at the end of this sentence, pre is the beginning. So till now you will be just going left to right and mapping everything. But now that is a problem. You have to ignore pre till you have covered these. Okay. Yes. Yeah. So you have to Yes, bidirectional. Again, bidirectional is at a lower level. At a higher level, what? Forget about neural networks. If you had to write a while loop to do this, sure, you're again going down a little bit deeper. So, sure. So that is again, there's a reordering involved here. That's what I was trying to get. And you have to decide when you're going left to, suppose you're just going left to right, you have to decide when to reorder. That this, or other way to look at it is when you come to this point, you have to pick which word I'll translate next. And it won't be the next one, it would be noble. And when you're here, you pick this one and this one and this one, and you're done here, then you go back and pick this one. Sure. Yeah. The underlying problem, or the catch, is that the word orderings in these two languages don't exactly match. So you can't just simply align them. Alignment is the and you have to. Okay, some more examples. Did you have lunch? This is, I just cut paste from Google, and I can't read Kannada, Malayalam, I can read Hindi. So now you can pick your language and try to do the same. You'll see that. So here the word ordering problem is, so this is a noun, and this is sort of adjective, or there are better ways, better forms of that you can, so it's roughly adjectives. And so it's a noun adjective reordering problem here between English. Here you have kya maps to did. You have, so you maps to aapne, aap and ne, there are other issues there. Have lunch, reordering. So the problem with English versus most Indian languages is the subject, verb, object. English has subject, verb, object. Hindi has subject, object, verb. Okay. And right. So I think I understand, but there is a problem with the encoder sentence embedding thing that I'll just next slide will come to it. If that could be done, then if that embedding captured all the information about ordering and everything, that would be great. But that's where the problem, it doesn't capture it. And maybe you can test in your own language if it is one of them, or the SVO problem, subject, verb, or object problem is ubiquitous across. Yeah. So this is just to give intuition of what the, so we'll be using encoder-decoder here, and what the encoder-decoder has to struggle with in doing this translation. Okay, this is talk about decomposition. You can ignore this, but so those who can understand it, T is the target, S is the source, and given the source, you want to guess an alignment. Alignment is what I showed here. Okay, this thing is aligned to this. So phrases are aligned, not just words aligned. So you have to pick phrases and pick phrases to align, and pick the target and the alignment with the highest probability, and that's your. Okay, and how do you do that? It's basically you look at the source and target. I mean, essentially what that diagram, you try to compute features for pairs of things. You try to match this with this and see how much probable is that. You might try to match this with this, and you end up saying that these few phrases have the highest probability. Okay, these are again rule based. If you had to do it manually, what is called the statistical machine translation. This is the old approach, which I mean, that's how it used to get done, and still there are these, till recently, these rule-based approaches were the most popular ones. And how did we go? This is, I think, Spanish and English, and to convert this Spanish to English, we started off with a aligned phrase dictionary. This is computed from, say, Wikipedia. So Wikipedia has language, like the whole data is in more than 300 languages, or maybe even more. So if you have a English Wikipedia text on Donald Trump, there is a Tamil, Telugu, Hindi, and so many languages also. So there is a one-to-one correspondence between sort of each sentence. That's a huge, what is called a parallel corpus that can allow us to learn. So you take such a corpus and then try to look at phrases. Try to look at phrases and see which of them generally occur in two sentences which with high frequency, and you compute such pairs and with probabilities, how probable these are. And when you try to this is called a phrase table, and when you so and then I mean, this is the decomposition of the problem. I'll just tell you what is written intuitively. So you start left to right. You try to pick a phrase here and a phrase here. Is just a word here, which has a high probability existence in my table, previously existing table. So this table is my sort of oracle. Okay, so in this case, V and null is a pair. Okay, we are done here. Again, in this case, you do. Okay, so essentially, you try to split the sentence in parts so that the lookup in the table is high. And if you go all this far, you realize that for this pair, there's what is matching has less probability than this one. You just stop here. So roughly, and there's more. Okay, there's more stuff there, but let's skip that. Okay, so did I? So there's this metric called blue, and so I'm before jumping to how we. So I talk about the phrase table based translation approach. We'll talk about the neural way of doing it. But suppose you have a system that translates. You have to monitor how you have to have a metric on how good it is performing. So if you have given this sentence, this reference, and the automated system is outputting this, you want to give a quantifiable number, a score to this translation. And when you average it over the whole set, you will sort of know how good your translation, a metric for your translations. Okay, and blue score is the popular score, which now the thing about so if you are converting images, classifying images to cat, dog, whatever, it's pretty clear to human being, most of the human beings unambiguously what is it. But here with sentences, there are multiple. So if the machine produced, there is a cat on the mat. Okay, this suppose this was the reference and this is what machine produced, you would still be okay. I mean, this is the right translation, even though it's not an exact match, still a right translation. So that makes the problem of checking harder. Okay, and so there is a scoring system. Essentially, you instead of matching word by word, so this is a bad translation and weaker translation system. Instead of matching word by, you try to find small phrases or bigrams and try to see how many times the phrases occur here and how many times they occur in the reference. Okay, and you try to take a ratio of that. Okay, so that the cat occurs 2 times here, the cat on the mat, this thing. So this is a sort of valid phrase which happens here once. Cat the never, it's not a valid English phrase in most cases. So cat the doesn't occur in my reference, 0. So I have generated a number of things. So all of these are ones. I have generated these twice where I would have expected just one, and this is generated once, whereas it shouldn't have been there. So this sort of tells you and you sum this up and sum this up. This is 4 and this is 6. Okay. Yeah. So and so the difference sort of tells you that all the phrases were not, either they were over generated or they were lost. Okay, and this metric is, people are not very happy with this metric, but still this is the one that comes pretty close to human judgment, so people use it. And Jeremy Howard, if you know, doesn't like to discuss this metric because it's a things are awful, but Andrew likes to discuss this, so I got the slides. Okay, sorry. So you get a percentage score. It will be always between 0 and 1, or yeah, and you want higher. So a perfect match, suppose you try to match this with this, whatever n-gram you find here, whatever phrase you find here, you will find it in the target sentence also, and exactly the same number of times. That's where it's what the boundary is all set, and you want to maximize it. And typically the percentages are in 30s and 40s for good machine learning translation. So that's the two. Normally we work at 80 and 90s for image, but the reasons being that exact match is difficult, so you have this approximate heuristic to match it. Plus the machine learning translation system for longer sentences, generally most of the popular ones don't perform that, and even the Google one is on the yeah. So that was the curve I showed in the beginning. Yeah, so it's around 30 and 40 for the best ones. Yes. Okay, so that's a rough idea. You find phrases here and do a rough matching, not exact. And that's a metric once your translation system. This is not what is used to train the translation system. Translation system works by matching word one by one. I mean the training objective of the there's an expansion to it. Bilingual something understudy. It has a meaning why it's supposed to be an understudy of the human being who's doing the actual testing. So there are a number of metrics like that. This is one of the most popular. Yeah, and that was the basic one. And there's some penalty for if you're trying to generate 2 short sentences, there's a penalty to make it bigger. Anyway, so yeah, without blue, you can't measure how good the system is. That's why it's essential to know. Okay, so we are back in the neural world. Okay, so I think it's a 2014 paper, sequence to sequence learning, and this should not be unfamiliar to you at this point. He loved to eat, captured into a sentence embedding, and then that embedding generates the sentence. Okay, again, if you go step by step, you take this word, embed it into a vector, encode. Is the LSTM or RNN working here? It combines meaning here. Okay, once you get this compressed meaning of the English sentence, you try to generate this, I think, German sentence. Yeah. And the way you do it is you put in a start symbol. Okay, and this generate the first word. Okay, how you are able, because this now that's why I talked about this phrase alignment. This thing has to do the phrase alignment inside. Okay, that's the catch. In the yes, the whole machinery has to, the encoder has to help the decoder to do the alignment in some way. And now so R should be aligned with he. So S has some information corresponds to all those 4 words. Okay, very abstractly. Now to generate the first word, this should know that it should use the information related to he and generate R. Now once it has generated R, it takes in the same generated thing as input. This if you know about language modeling, this should be pretty standard. Okay, once you take R and you get the compressed representation, you should be able to generate this. This corresponds to loved. Okay, so the machinery has to somehow focus on the part of S based on the previous word generated and the current S and the initial S, partial S. Right. So at every step, again, I'll go back to the while loop sum. Sum is transformed at every step. S or H is transformed at every step, from here to here and from here to here. Okay, this is sort of initial biasing of the network with that knowledge. So again, the hidden, this is the input, not the layer. So there is input and there's a transformer. So input is this. After transforming, you get an embedding. Transform, you get an output here, which is the embedding. Transform. Yes. No, the S is also transformed here. So yeah, so it's probably necessary to go into how, but again, I tried to avoid getting into the internals of S, but F H t minus 1 X H t. If you remember just this, S is being fed here. X is air. Okay. And there's this internal holes and transformation which give you HT. HT is not shown here, it is here. And it also, there is another, call it G, which takes maybe HT minus 1 and X and gives you. So for the encoder, that is X. For the decoder, it's the word in the target language. Okay, so they are both RNNs. They both have those same equation, but what they have different tasks. This guy has to compress the sentence or encode it. This guy has to generate new words. Okay, so their machinery is. Does that clarify your question? Or? No, it S.
The transformation only happens here. Does it happen here also?
So what goes here is HT. So S is this. It's transformed to HT. At every step, it's like the sum plus I happens at every step. Okay, so so intuitively, it also takes into account what was inputted earlier at every step. Here, S knows that all this was input, besides the fact that the input translation. Okay, and we are next slide going to break this single S into several parts, so that will be more clear. But that's the okay. And again, there are more details here. The output is not a single thing; it's actually a branch over all the vocabulary, and the word has the highest probability. And what is called the softmax layer essentially enables you to normalize among them, and then you pick the highest probable thing. Okay, so doing this, if you have a 80,000 word vocabulary, this thing needs to be done very efficiently, and there are many tricks to handle large vocabulary. There are steps, yeah. Yes, so RNN cell is just this. That's why, and you have to repeat it. Yeah, but there are again variations. You can have stacks of these cells which could be different from each other. And so the hidden state typically is 512 1,000 real numbers. You can calculate your memory based on that. Yeah, and but it's not just the 1,000. There is generally much more complicated inside it. So it has to. So one way for it to know is to look at this dot, and so it has to generate the end of the sentence. So, and it also, when you're feeding in data, it also learns to recognize when the sentence ends. That's part of the learning. Leaped, yeah. So it's like in probability terms, it's like probability of y2 yes and y1. Yes. Yes, we have to be more careful with the decomposition here, but please go ahead. Yeah. Yes. Yeah. The encoder thing, that should be
only a function of, for example, English language, or is it like also has the learning when you try to do the training?
Yeah, so what it learns here, the meaning of,
It learns with the encoder or LSTM.
yes, so maybe if I try to answer the meaning of, it has to capture the meaning. And loved her versus loved to eat are two different things. So it should learn enough stuff by combining these two word vectors to distinguish whether it's loved to eat or loved her. Not clear? The context, yes. So it has the responsibility of, it has to learn the context of. So each word may have some meaning in its own, but when it occurs in this particular sentence context, it can assume a slightly different meaning. Okay. Hmm.
On the like other project, like what I call like trying the NLP network, like encoder and decoder. Once we have Latin, for example, we train it using like English and German conversation.
Mhm.
Then we can keep the encoder of the same language. Then we can replace it with some private Tamil
Right.
decoder.
Right.
So if it's going to work, then it means that encoder learning happens somewhat like in front of whatever is there in the decoder.
Yes.
When you do the training process.
Yes, so that is multilingual translation, and I mean you try to use the same network to do multiple languages. Yes. Normally you will, we will come to it, but the short answer is that if you have to use the same thing to encode multiple languages, you have to have similar representations for the words that are going in the vectors. So these words, although mean different things to us because we know different languages, when you map them to vector spaces, you can do it in a way that all of them similar meaning stuff in different languages are a cluster. Okay, and that will help you use the same machine. But that's where a lot of research recently has been done, and it's sort of cutting edge, right? How to do that efficiently. Yeah. So this is the output. No, it is the just this sentence, this sentence. Y- Yeah, so maybe you should. What is the question? If you think of this network as the black box, what is the what do you give at sort of every step? Yes. It- Yes. 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 Right. So there are many questions in there. Suppose first of all you have a pair of sentences that you have, that is your starting point. The lengths might be different. One simple way, just fix a max length, add some padding, max length. Okay, then you first you just encode this, the whole thing, get a vector, and when you start generating output, you just give this the output sentence. You don't worry about aligning it. Expect the network to align it. Your yes. So maybe if I draw this diagram, this is my sentence, English sentence. Okay, just call it a. Suppose this is just one word, and I get a D y hat is a predicted output, and I know the corresponding y for this word. So you can, if you want an arrow like this is also there. Okay, and when I get this, I compute the diff. Okay. So the output here is actually the word. So the network converts. So at this softmax layer, the you have, yes, and then you pick the best one.
How will we find the diff towards
Then you pick the best one, highest probability. That's an index that corresponds to some word in your vocabulary. Now you've gotten word. Now you have a word that is predicted. You also know what is the next word you want to be predicted. Could be the diff. Yeah, and it's not exactly. I mean, there is a more mathematical way of doing exactly this.
contest again?
Sure. In general, the context is very important. Yeah.
I understand like
So let's go ahead and maybe things will be more clear with, because we are going to change the.
the multilingual content have the same as
How to do multilingual translation? There are several ways, but we'll get to it. So if this is the diagram that makes makes it clearer, this is a sentence, word vectors corresponding to it. Actually, so now this is complicated, and there are a number of layers that process the word vectors. You get the encoder, and this, what you get here is S, is a concatenation of this. You feed it into the decoder, this thing, that becomes this thing. I'm not sure it's the same or not. You feed in the first word, which is EO, and it should be beginning. Which should be beginning of string, I think. Yeah, beginning of string. You get one output word. That word is fed in here. That generates the next output. When you get this output word, you have a sentence here. You just match the first word with the first. Match the second word with the second. So you force the network to generate the right sequence of words and the right words. And if it's not, you flag an error. So it goes, so the way the machinery is set up. So we haven't talked about how it learns the weights and all that. There's an algorithm called backpropagation. And essentially, we have set up a series of transformations, get the output, get the loss. There's a way to propagate it back in a very mathematical way to every weight and change it. Okay, and that's what the backpropagation gradient-based learning does. We'll have to.
I think the expression here is that probability of the should be high, so that corresponds to the network would give some probability to the and that difference is then backpropagated.
That's right. That's the error, and error is backpropagated. Yeah, and if you're guessing something. Yeah. So yeah, so there are quite a few moving parts here. I mean, you don't, generally it's not advisable to look at this complicated and think about backpropagation. You should maybe start with the simple feed-forward network, and actually you can just write all the backpropagation rules. So again, there is more detail in the output. There's you since you are generating several things, it's like this is the word the, this is the word blah blah. You're generating several things in one go. You can sort of think of multiple possibilities. You can pick the first one here, second one here, third one here, fourth one here, or you can fourth, third. So essentially you can, this structure or this setup allows you to generate multiple different strings. And how do you pick the best ones? You just compute their combined probability. So if this path has higher probability than this path, then you pick this one. Okay, and you can pick K or N top. And that's why the beam has n top. So, or based on the number of n you want. So you can just, whatever, there are 4 cross 4 cross 4 strings here. You pick the ones with the K ones with highest probability. And again, this beam search is a very old, I mean, it has roots in HMM and yeah, what should I call it? More structured space search. and it can get, this algorithm is also pretty complicated, and there are many variations possible to, depending on what you want to generate or how diverse you want to be. Right. So context, if I just say context, so if I probably some examples will make it clear, but if I hadn't generated I, instead of that I generated we, the first step, my verb will change at a later point. I have versus we, okay, you, yeah. So the next words, although I will, you have, I have, we have, give me some, she has, okay, she has, but he has also. So if, so he has is in some way similar to I have, okay, but so, but if I generated I should generate that right, and so that's why this context is important for them. And that's just a very simple example. There are a number of cases there. So yeah, and I'm going to break the single thought vector model with this slide. So now these are all diagrams which look similar, and I'm trying to do a variation based learning on the audience so that you get to get the meat of it and not stuck on the, so in input, embedding, I talked about by LSTMs earlier, right? In general, the first. So these diagrams, I'll actually get to the Google NMT, Google Neural Machine Translation Engine. That was, so I talked about phrase-based translation. What you see on Google Translate till 2016 September was phrase-based translation. It was working pretty good, but so this research happened in the span of I think 1 or 2 years, and it was so successful, and it outperformed phrase-based translation, and Google put into production this variation of this engine with several optimizations in 2016. The whole Google Translate was sort of swapped with this completely new world thing. So just yeah, it was both in terms of how quick research reached production as well as the amount of performance gain that happened that convinced the whole organization to make the switch. Okay, so maybe, okay, the key, we are trying to, till now we are trying to capture the meaning of the sentence in a single vector, which is I mean, pretty stupid thing to do, okay, because there are a number of reasons there. One is that this transformation of the last word happened much closer to this generation of vector as compared to this. So you would sort of intuitively expect this information might be more lost than this one. Even if you do backward, the middle information might be lost. All sorts. So even though we want to compress the information into vectors, it turned out, or people realized, that having a single vector is not good enough. We should just have one vector per word. So we still have the encoding process where the initial word embeddings sort of, they are juggled together, and you compute the final embeddings or final representations of each word. There are 4 here, 5 here, and 5 here. Okay, but now instead of a single state S, you have this split encoding of the sentence, and this solves that. So I was talking about, at this point, when you see null, you should now aligning things become more intuitive. Okay, so when you see null, this is the beginning of the sentence, you sort of, the machine can normally can automatically try focusing on the first word. Okay, and if it is successful, the word at this point, it can, now since it has these 5 representations for these words, it can see that the word is closest to this one. Okay, and so maybe the next candidate is the word loved. So maybe I should try to translate loved. Okay, that's trying to give a rough intuition of why this splitting is. So the problem, so it's always good to think of it in a rule-based way. We had to map phrases to phrases, and the architecture, the previous architecture, was sort of doing it magically. There was we hadn't architected it good enough to do the alignment explicitly. Whereas this, if you split it, then there is a way to align what you generate with words here more explicitly. And that is called attention. Okay, so attention, well, although we have come to that concept in this particular fashion, it's a pretty generic concept, although this paper brought it to the front. So whenever we look at an image, or we focus on some parts of it, we don't focus on and that's how we recognize whether there's a cat or a dog. The network should also have the ability to do that. If it does that, it will be more performant, it will be more effective. That's sort of capturing our intuition into a network. Now the previous architecture didn't. By adding attention, and I'll tell you how exactly, we are able to focus onto different words in this first sentence to translate.
This is a vectorial sum.
Yes, it's a there's a dot product going on there. Dot product has the plus inside, so it's all will boil down to dot products everywhere. So wi plus wixi sum. Yeah, and there are w's here and there are x's here, and which one to weight more is the attention weight, in simple words. Yeah, we'll get there. Yes. Yeah. So the starting word is always fixed. It's the start of the string, or beginning of string, and then you are whatever comes out as the output is passed in. So the responsibility of the network is to get so initially it gets awfully wrong, and then so you have to train a huge amount of data, and after some time the holes get filled in such a way that you start getting the right words or the nearby words. That's how the so vocabulary as such is fixed. A huge, you take 40,000, 80,000 for the real ones, and you assign numbers to it. So you have integer IDs for each of those words, and what you generate here is one integer ID, which is the highest, and that's converted. Okay. So the matching happens. You take 10, convert it into the word vector. You also have vector here. So we are jumping ahead, but I hope audience is coming along. So you from you have to, looking at this word, you have to learn to focus on loved. Okay, so you take the embedding of this, which is a vector, and you match it with the encoded versions here. Yeah, and then you figure out that it's closest to this one, and there's some logic which tells you to focus on the next one. Yeah, so the matching, that's why boiling everything down to the vector space helps you just do the dot product and do the matching. So dot product and weighted sum, that's all that is going on. Can you I just illustrate the same thing. I am a student, J, Z, Ya, Zui to the end. Okay, and this is encoded into vectors here, and then when I'm at the first position, this beginning of sentence, this thing I feed this, or the encoded version of this. So I encode this part also, because this is just a string and I have to convert into vector. I get a vector for the first decoder output and a set of vectors for the encoded. I match this vector with all of these. I find that this one has the highest weight. Okay, so that means that I have to translate I now. Okay, and there are a number of things going on. Maybe you should ask the question. Yeah. Yeah. Right. Right. So reordering means that it's very simple to model reordering. I am, suppose the next word, I want to focus on a student and not I. This attention mechanism will just have this highest weight, and that will pick up this. Okay, so the reordering is automatically captured with this attention. Yes. So at every step, you compute the attention weights, and there's minor thing. So how does the math work? Is these are not, so intuitively you would think that you just pick one word. Why do you need to have weights on all of them? Okay, you just want to pick one word which we translate, but that breaks the continuous modeling or differentiability. So what you do is you have a whole, you score everything like you do with probabilities. You scroll everything, and the one that you want to most focus on gets the highest weight. Okay, and then if you have these encoders E1, E2, En, you have the weights W1, W2, Wn. These weights are 0.5, 0.3, and these are the encoder. You do a dot product, which is Wi, Ei, sum. Okay. So you sort of combine. So this is again a thought vector being computed at this point, which is a weighted thought vector where the weight of this thing is highest and others are. So the machinery doesn't let you just focus on one word and just filter out other, but it indirectly, to keep this continuity of expressions, stay in the continuous domain of functions, you weight one of them higher, and the output that comes out, it's actually called the context vector now, and I think it makes sense intuitively. The context vector contains most from here and less from there. Again, that context vector is now used in the decoder along with the previous hidden state and the current. X, H, C. X is the input, or maybe here X, previous hidden state, and the context. Together get, and you compute the next output. Okay. Yeah, the context vector is a weighted thought vector from the source language, if that makes sense. Attention vector is also computed on the source. Which word in the source language you want to translate next? That's what it answers.
But that depends on, like, for example, SVO target language is different.
Sure.
So that's the thing which affects the
So
attention weight.
yeah, so what the number of things that determine what they should, including the language, including what is the last word, including what has been translated. So everything that was affecting earlier, the hidden state, plus the similarity between this thing and the encoding. So the embedding of these two. Okay. So yeah, so again, attention is, again, the basic idea is just weighted sum or a dot product of you assign weights to the encoding. But the way it is used, and it gets more complicated. The way you get more complicated than a simple dot product to compute the attention. So it takes some time to fully absorb it. Yeah, I have a more step-by-step. I'm not sure. Yeah, so maybe just in formulas. You have the encoded sentences, E1 to En. You have the current decoder hidden state, DJ. Okay. You compute pairwise similarity scores. I call it similarity, compatibility, whatever you want to. That's a very vague notion of what happens there. Of DJ, the current decoder state, and all the encoder states. Okay, you get a vector that is pairwise length for, or length of the number of encoded sentence. Then you normalize these scores. If you're familiar with SMART, it's a weighted. You try to bring it down in the range 0 to 1. Okay. And use, these are my attention weights that you're seeing 0.1, 0.3. and then you weight the encoders by these attention weights, you get the context. The context is used with the current decoder state to compute the next decoder state. Okay, so it's a quite a bit to absorb quickly, but I hope the intuition is coming across. Yeah, and generally, if you start writing these AJIs and number of indices increase, it's goes out of your head. If you can instead write in terms of vectors, take a E vector and do a vector softmax, and then it becomes cleaner to write these things. So since the introduction of attention in that paper for the task of translation, attention has spread out to almost every task that people want to solve. And so you want to classify, you want to focus onto a particular word, like the mobile example. So instead of just chucking along and computing the sum of the embeddings, you want to put more weight on the words that are more important and use them for classification. So it has gone to image or speech everywhere. This encoder-decoder model with attention on the encoder outputs is just ubiquitous now. Okay, this is just, yeah, I mean, these are the encoded vectors. These are the attention weights. This one is the highest, and do a dot product and get there's a nice way to visualize things. So attention also gives you now interpretability into the system. Okay, what do you mean? So when you're looking at the thought vector encoder decoder where the symbols, you didn't know what was inside that state and how the translation worked. Now with this attention to every step, you can see, oh, this is the word I'm focusing on most. So if I'm focusing on the wrong word, it gives some insight into the modeler to correct. And this is the sort of confusion matrix is a general metric for the output, matching the outputs. This is attention. Huh? Attention matrix, yes. And it's very simple to read. I mean, if you stare at it, you'll just figure out what is going on. This is French, this is English. And S, she is matches with A here. Anne's matches with 5. Sorry, 5 years. Huh? Yeah, so the color coding is so if this is white, it's near 1. This is a very black and white model, so maybe it's not a good one. So these are the highest points of attention. So every word, when I'm trying to decode here, I have to choose between all these words to focus on. And so I have an attention vector like this, and this is the highest point. Yeah, which is white. So you just, normally these diagrams are in color, so you get much better. So generally there are multiple words that are focused on. Okay. So if I have communicated the idea of attention to you, I'm not, yeah, the material that I have will at least take a few more hours. So I'll go into a Rajdhani Express mode and just, so instead of the simple dot product mode, you could have more complicated functions which take the Q and K. Now I'll change from decoder state DJ to query and encoder state to key. So whatever you see in encoder are the keys. Think of hash table now, okay? Are the keys, and output, the decoder is the Q. So the query has to match with one of these and pick up its value. It makes sense. Okay. I think we will do something. Yeah. Thank you. So you have to compute a matching between Q and K, and you could design all sorts of complicated function to that. Yeah, query and key. I'm generalizing it from the encoder-decoder states that we were talking about. I'm calling the decoder stage the query, because this is what is my current state, and I'm querying into the encoder states and trying to figure out which is the one that I need to focus on. So I call those the keys. Okay, actually the keys and values are both the same there. But so you have to, yeah, now you can switch to this mental model. The query and key has to match and compute a new value. And across years, yeah, this is a more linear additive kind of model where you do additive combination of Q and K. This is where you multiply Q and K and try to figure out. So I mean, understanding these will take some time. But the simple dot product is always there. You do a simple dot product, you compute a score, that is the attention score. Okay, and there's a scale dot product also. Yeah, so this is a snapshot of the Google NMT, which was actually deployed, and they wrote a paper nicely to explain many aspects of it. It has 8 encoder layers. So the complexity of, so initially you encode, this is the actual system, or probably very close to it. You take an input sentence, you encode it here, bunch of encoder layers. These 5 representation of vectors are the refined or more abstract representation of these 5. This is what we work with, the keys. Okay. Decoder again has these 8 layers, which I think they are only forward. And it's very carefully designed, every part, why they have chosen that component, what are the inputs that feeding it, everything has been very carefully designed. And yeah, and so when you generate it, the basic mechanism is the same. When you generate the next thing, attend to one of those words, and that feeds in. Okay, why you need these 8 layers is essentially you want to capture the context of the sentence properly, the words occurring together, and these layers help you come up with better representation of the word, which will actually help. So you actually you want to both capture the context of the language as well as make it the target language friendly, so that when you match this, there is a similarity. And
Based on the language encoding also.
yes,
The target language. Here
yes, that again, this architecture is not different for different languages, but yeah, how should I? Yeah, I just said, yeah. In general, we have multiple layers because, the first layer can learn the matching between, say, he and loved. The next layer can love. The long-term dependencies are better captured at this layer. That is one of the reasons. Yeah. Yeah. And yeah. Yeah, I don't see convolution here, although there might be something. These are all recurrent layers. Yeah, but it won't be a surprise if, I mean, too different from, you could easily combine convolution with recurrence here. And sometimes this layer, yeah, so I mean, so this is the paper which is not visible.
Capture the differences between the layer captures the differences.
Better between. So you can, one way to think about it is that it refines the embedding of each word by incorporating context from. Yeah. And yeah, one of the issues is that all of the stuff happens inside by these geometric transformation W, X, and so interpreting them is very ad hoc. I mean, after doing lots of experiments, people come up with their own interpretations, and then everybody sticks with it. But I don't think anybody knows what is exactly going on there, which is one of the problems with, although these neural networks perform very well, if they don't perform well, or if you ask why it gave this output, it becomes hard to answer those questions. Softmax is just the normalized sum modified. W1 divided by W1 Wn. Okay, this is the, if you have W1 to Wn, yes. So this will put all the values between 0 and 1, and a small twist to it, exponent, that will raise the higher values even higher. You still get the thing between 0 and 1. So yeah, that's a popular, because of its normalization property and exponential, it's the popular layer at the end, where you have these 5 categories. You have the weights for these 5 categories, and you want to bring them between 0 and 1, and then pick one of them. Yes, it becomes the by doing the normalization, you get the probability. Is that? Yeah. No, it's not. Yeah. No, it is just the normalization operator. Okay. Yeah. So, I mean, the one property of this, so we'll get into the multilingual business, but yeah. So since they found that it was working so nicely for several languages, they threw more languages at it. And so, now this diagram needs to be, so they had one set where they translated English to Japanese. They had another set where they translated Japanese to Korean. Okay. But there's some modification that you can do. Essentially, you can also add, besides the sentence, you can add the target identifier. You can say that if you want to transfer, you add FR here, okay, or Spanish. So that way you can now use this architecture for arbitrary pair of languages. Okay, but yes, personalized to the language, yes. And by doing that, they train the same system. So now earlier we were stuck to pair of languages and the data there, and one network for each pair. Now this generalizes it. For several pairs, you have the same network, meaning the same weights, same holes. And so it gets to learn from so many examples. And now the advantage that, now if English to Japanese is working, now suppose you don't have English to Korean, but by transitivity, you can go from English to Japanese, feed it as an input Japanese, and go to Korean. Because you have trained these networks to capture Japanese Korean well and English Japanese well. Okay, so I mean their selling point was that we haven't seen we don't have Japanese Korean translation data, as much of it. We have very little. But because we had a lot of English Japanese and Japan, sorry, I am getting confused here. And English Japanese and Japanese Korean data, we were able to get a new kind of mapping which we hadn't seen before, and that performs not as well as having the original data, but relatively good. So yeah, so that is very cool in the sense that we can call it transfer learning, call it reusing all knowledge or multiple sources of knowledge into a single box. That thing is very useful for building general systems.
Basically, if you have prepared the language,
Yes.
not ordering the what is being more language, what is
Yes, so it has to. Yeah, so language identifier helps you attend to that identifier also in coming up with the next word. You can think of it. If it is a word ordering that it has to capture, it has to do it through this attention mechanism. Yes, so they have a single train network for all these languages. Oh. Okay.
So am I finding that some of these parameters are similar in just as in image processing, the earlier layers are lines and
So if you're asking what these layers represented, no.
earlier layers are similar for images.
Yes.
Earlier layers are similar.
Yes.
That's what they observed, and they could rate it. In the language modeling, if possible. Like from English to Spanish, I have one trait. Another is Japanese to Korean. Yes, so is it there? Are the earlier parameters similar here also?
I don't know, and I don't think I've seen something like they yeah. So I don't know. interpreting these networks is harder over text than images. You can see stuff, and those kernels are somewhat similar to here. The other ways to interpret it, sometimes they figure out which word is giving more. Some of the neurons correspond to some types of words. There's some other interpret, but in this I haven't seen much interpreted except attention. You always know what you focus on, and that helps a lot. Okay. I'm not, I mean, there is stuff to cover, but I think so yeah, we have been talking about words, characters, something called byte pair encoding, where essentially you can have a fixed vocabulary, and then there'll always be, you move to a new domain, you'll have new words. And what do you do then? You start, saying that I don't know this word, I do this. That's what OOV output is, out of vocabulary. That's the output that if you don't recognize. To avoid doing that, there are several tricks, but there's a more systematic way of representing words as combination of their parts, and that is very effective in these. It's again started from the translation architectures, and now it's everywhere. Wherever you want to handle newer words in a seamless way, so there is had some slides on the algorithm. And this is a 17 paper, which is, I think, has so we have made some assumptions. So earlier we were stuck on the thought vector. We got rid of that, and we have a split representation now with attention. Now we had another assumption of the recurrence, having a recurrent layer. There are problems with recurrence. Essentially, the sequential. You only compute the next thing after the previous thing is ready, and that stops parallelization. Okay, you could switch to CNNs, but then CNNs have the small window. You want to look back, long back. So there are tricks that you can play with CNNs and dilated CNNs that can help you. But yeah, so these guys, a lot of people wanted to get rid of RNNs, and they were trying to figure out a good architecture for it. And this transformer architecture, again from Google, and it's probably the state of the art architecture for machine translation tasks and for other tasks, is what they came up with to encode the sentence and do the transfer. Essentially, it doesn't have recurrent units. It has only, every word is, I'm not sure if you have, yeah. So every thinking machines are 2 words. You just encode this through a layer called self-attention. Okay, attention is again. So paper is called attention is all you need. Means that throw away recurrence, throw away anything else, and we can live with attention, and we can. And this paper actually outperformed all previous, including the Google NMT architecture on the translation task. So they invented this thing called self-attention. They didn't invent, there was previous, but they incorporated it. And so essentially what it does is incorporate the context. So RNN, you go left to right, you are incorporating context, and if you're too far, then start from right to left. And that's now in hindsight, it might seem like a very inefficient way of doing it. The self-attention essentially, tries to combine. You think of a data flow happening from, you have to compute this, combine this word and this word, and compute this. Compute this, combine this word and this word and this word and this word. A more parallel kind of, what's the, there has to be a more of a merge operator over all the words. Okay, and just every step merge. And by using the attention on what to merge in the next step, they get good representation. So this is the building block of that architecture, where you sort of merge the context, compute this representation, normalize, feed forward this. So data, except the transfer happening here, it just goes forward. And so for the rest of the sentence, you can also mostly go forward, except at this stage where you have to transfer information. So it reduces instead we were earlier going from left to right, step by step. And if there are 10 layers, this layer computes, and then the next layer works, and then it's extremely horribly non-parallel sequential architecture. So yeah. Yes, it uses all of them and uses them efficiently. There's essentially another dot product happening over these. Yeah. Right. But convolution has a fixed window. I think that is there. Yeah. So convolution has a fixed window. This guy goes anywhere. The drawback is that you know the exact weights associated with every guy. You know where the information came from. Whereas here you compute these weights dynamically through attention. And so these weights, you don't, after you sum them up, you don't know uh, where they came from. So that causes some loss, and then there are ways to, yes, localization has been lost.
Very simple, right? Looks like simple training. You
Yes.
don't have RNN, time difference.
Yes. So if you think that RNN are a dangerous beast or very hard to handle, which if you try to implement them or used to in the earlier versions of TensorFlow, you used to end up doing lots of small things to set up a cell. So this takes away a lot of pain, right? A lot of things, but RNNs now I have to go back and defend the RNNs, that this automatic merging that was happening, the context, that has to be sort of recreated in the self-attention layer here. Plus, you have to record the positions of. Okay, so there's so in RNN you automatically know that if you have run 4 steps, you have covered 4 elements, and you know the distance between 2 elements. Here, if you just run everything parallel, this word doesn't know how far it is from the other relevant word. So you have to incorporate that information also. And there's a thing called positional encoding, which does it. But anyway, I mean, it's good to just see some visuals. And so, yeah, maybe for the rest, for just to back up, I introduced attention from decoder to encoder. Okay, that was a cross attention you can go. This is self-attention by name. It's happening inside encoder, and it's happening inside decoder also. So what basically it's doing is, so this is one layer of the encoder, next layer of the encoder. Okay, the same words are getting encoded. You have embedding here, embedding here, embedding here. These are being, so if you look at the embedding of it here, these arrows tell you where it focuses on. Okay, so the animal didn't cross the street because it was too tired. It learns to focus on both it takes a while to interpret both the animal, this is dark animal, and tired. Okay, so when you had the initial embedding at the bottom layer, you had the words embedding for animal and cross and street, and because those were sort of independent embeddings. By doing this multiple merge operations, self-attention, what happens that it learns to understand that it actually refers to the animal here, and the embedding of it captures the information corresponding to animals and tired. So it captures sort of the you can think of an average of, that's not fully correct, but the embedding of it will become an average of animals embedding and tired's embedding. And that's the way it captures it merges the semantic. Only this sentence, only this, yes. So at one time you just see this input and output sentence. That's all you see. Going beyond that is a separate problem. There are other ways to look up knowledge bases and all. Yes, it is. Yeah, I mean, I'm not sure if I have the equation. Essentially, the idea is that you have the embedding for it here, call it the query. All other embeddings, call it the key. Match the query with the key. Wherever you have the highest matching, highest weight. Okay, so if you do that matching across, you'll find that weights here and weights here. Maybe not in the initial layer. This is the layer 5 when it has learned some stuff to actually focus on the right thing. So it's just again keys and query matching. I don't know. Thank you. Okay, I am trying to just wrap up now. I think. Yes.
Already language translation, Google stuff, to an extent is accurate. And with this parallel networks, trying to do searching.
Yeah. So this is just, it's 18 and 17. So getting it productized, people understanding it properly, improving that is all going on. Yeah.
Mostly performance optimization. The way I understand self-admission and all this stuff. So accuracy, I've not seen any much improvement. Only thing is that performance-wise, sequences.
So both. So
understand
Mhm.
this machine neural machine where is it going?
The short answer would be multilingual. Multilingual, trying to do it, not having a encoder decoder for every pair, but for having one universal encoder, one universal decoder. That's the sort of holy grail, and people are trying to get there. That's what. To get to that, you have to solve several sub problems, including performance, including getting data, and this is just static translation. You're given one. When you look at a corpus, when you have people involved who translate, there's a whole industry of people translating stuff. There are other problems that how do you fix these translation if they are slightly wrong, because these systems will always be, at least now till now they are being. So how do you fix them very quickly, and providing user assistance to fix them through these networks. So we are just studying the core problem here. Bringing it to practice has n number of different variants of it. And
actually, I was understanding sentence, multi-language.
mm,
That single sentence something happening with that, and I would say that I'm part of the
mhm.
unlike something happening with that.
Right, so under the multilingual umbrella, that is also essentially what I've told you. Convert the words into vectors. That's the starting point.
So, purpose will be encoding the numbers might come say I use simulation thing like this. Encoding might match. This is the match.
Right.
Yeah, the source itself is a combination of multiple languages.
Sure.
So,
But
and I say I want to convert it.
Mhm.
See, there is third person we only understand. I know partially English, partially Telugu,
Mhm.
Kannada. I mix and speak.
Mhm.
And what you want is only English. I'm just
Mhm.
trying to understand.
Sure.
So basically, it should be converted into one language called English.
Mhm.
Is something happening in that? Thing?
So,
we achieve with this existing.
Do you think what I just explained can also solve the problem?
That's what I was trying to map. Actually,
So maybe just go back to the step-by-step architecture. The key part is getting from, if you have a sentence, you have to get in vector embedding of the sentence, and the sentence are different words. Different words have their own embeddings. You can just combine them.
embeddings itself, I think.
You don't like him?
What's confused there is it?
No, not confused. You don't like them. That's a different thing.
So it's not liking basically every language, every word will have its own embedding.
Mm-hmm.
So if I combine multiple languages, the embedding vectors might match the same word.
I think it depends on the corpus for which we are.
Yeah, the corpus is
So,
Yes.
if we have a corpus good enough for these multilingual sentences, we can come up with
Yeah, that's what I'm saying. Today we may
a
not have that kind of corpus. So because the corpus which are created to the best of my language are separate for every language. We try to combine all this stuff. With IC it's a different problem. See, basically I am from outside Kannada. And I'm trying to learn Kannada, I'm trying to write certain things. I speak basically part of my language and part of Kannada, and you only understand Kannada.
Right.
So I see it's a very good opportunity to kind of research.
That translation system could be.
Systems. It's eventually over a period of time I may be good at Kannada. Till now I'm part of Kannada and part of my native language I speak.
Yeah.
So
just stressing on it, it would be extremely useful if we had translation systems that are as on our mobile phones very easy. So I'll again point you to, so the problems that you talked about, different vectors and those are the problems to be solved, but the approach remains the same. How do you get vectors which are multilingual, and if the two vectors, two words across language have the same meaning, the vectors should be same. Yeah, so again,
if you see on Google keyboard, you swipe. So after a while, if you swipe in English also, it will predict the Hindi words. You keep on typing in that way. If you say "aap kaise ho," and if you swipe it like that, "aap AAP," it will give you "aap." So it is trying to learn on itself.
Mapping of word.
so I'm still say, did you get the?
One of the aspects is performance.
Mhm.
Doing inference or doing the how it is how much completely
Resources and yes. So again, all these systems are,
There are two aspects. One aspect what we are talking. and
yeah, all these systems are tied to what are called GPUs, because you have to perform these several big dot products across matrices. The whole thing is just set up on blah 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 blah. And to do them fast and on multiple sentences, you need to have specialized processing which GPUs provide. Right. So the effort right now, for example, there's a tool TensorFlow by Google, which out in 2015, and they have been trying to continuously improve it. The goal there is to compress the networks. Those big ones get compressed with minimal loss of accuracy, and they run on your mobile. That is where things are going. You can do that even right now for some very popular image networks, right? So the one that I showed, InceptionNet. So somehow there is a race, techniques in image processing with deep learning developed fast ahead of speech, and so there they are slightly ahead in compressing these networks with performance and getting them run both here and in a browser also. So browser, if you have a even simple GPU, browser has WebGL libraries and all that. So there is huge amount of work across. So that's why viewing this whole programming by example paradigm as a software 2.0 is helpful, I think, because there's a whole stack like a network stack or whatever, from compiler level to application level, being optimized by research and production as we speak. Yeah, and it's a very within the next week you'll see at least one paper on that problem. I'm not going to write. There are people who are going. I'm just stressing on the way the things are processing. Progress is happening. Yeah. So, and yeah. So this is one of the, there are English to German, English to French tasks, and it's sort of the leaderboard on. So before that, yeah, now it's all attention you need. That's the transformer network without the RN is the leader. Yes. So the field of machine translation is 1980s, where IBM had huge. There are several IBM models, the SMT. So the data preparation that was also is there. So the most popular and biggest, these are million lines of parallel. Million lines. So many languages have huge corpus, and the problem is just to absorb that into a network, which is for this. Other languages, English, Hindi, for example, there is still a decent corpus. But if you go to more, less spoken languages, there's lesser data, and you want to conquer that domain also. So effort is data collection is one of the key problems. So the statistical machine translation, the one that I showed you in May, you have these phrase tables. You build these phrase tables, right? And then you have an algorithm which goes left to right and tries to predict the next phrase to map to. And they are those algorithms are also pretty good. These algorithms outperform them, but they remain till few years back they were the state of the art. And still there are optimization done there which have to be learned from people are trying to improve these. Okay, so I think that should, yeah, we didn't go too deep into the transformer, but self-attention is this thing called multi-head attention, and so it gets yeah, it's all dot product sets of them. What do you attend to? You have to be yeah, and that's how you model the network to set that up is the
neural network and
Hmm.
image processing based neural networks and language processing.
Hmm.
So for image processing, you see like small companies like can work on it. In the sense like each image processing algorithm detection object anything is
Mhm.
depends on different field. Like they have to develop some specialized network. So they have some research. Companies can do their own specialized work.
Variants of the network.
But when it comes to natural language processing, it's very big one to enter in. Second thing is
It's a big. Sorry.
big one is like we need a lot of corpuses like data.
Which is true for image also and speech also. It's not different at all.
The thing is, Google is gonna develop neural vision translation.
Mhm.
It's gonna be the best, and there is no reason for a small.
So what about Amazon? If you worked in Amazon, what do you say? Google is the best or mine is the best?
No, once those things they are product. So once neural vision translation is there, like Google is going to do it. It's a generalized one, and the sense like there is no need for a small company to come and gonna outperform Google. But in image processing,
So I'm not sure that statement is right. Yeah. So because again, context, particular use cases, you might need variants of the. Just like for image processing, you are seeing that there's an object detector module which you can deploy on Colab, Google, or whatever, and just use it. There are often variants based on the particular domain you want to, small size objects, where you have to tune the network. So you slowly need to have a deeper understanding of what is going on there. Similarly here. So yeah.
question I asked is,
Okay, sorry.
the thing is, what are the things that other than machine translation, what are the other things that we can do with neural network and NLP? Like other companies are focusing on.
Actually, only one paper, one guy has written Srivastava, that paper is dropout. And one single paper has so much impact on all the deep learning. No, so only one person can take.
So I think he's asking about application domains where
Academic research is fine.
right.
But I'm saying about companies focus on NLP.
Yeah. So what you're asking is that I am not supposed to do self-driving cars. I'm not supposed to do translation. What is a simpler problem that they will not solve? And I can. It's a little. I'm.
I just want to know.
Basically, many things can be nine people. Each. There are many things you have to.
So it's mostly like image processing. I can easily find applications where like.
You want to find applications. So text search will keep you busy for years. So again, you have to capture the meaning of the sentence. That guy has worked for a few years, I think. Yeah, you have to capture the meaning of the sentence, and you have to do a proper matching. Then, if you are done, then question answering. Again, you'll have Google and others to compete with, but that's a seriously hard problem. Yes. Yeah. Yeah. So the question answering, particular domain question answering. These chatbots are trying to solve these problems in a limited context. This is a domain. These are the questions. These are the answers. How do I remove the human from the loop as much as possible? Those kinds of things. Those are, yeah. I mean, there's so many domains of application that there'll be stuff. Things don't generalize from one domain to another until you have that. There's scope. Yeah. Good. Thank you. I'll just close this. Thank you for presence and asking questions. I hope you got something useful.
Sure.